the host and share this meeting.
So hello everyone, we have Dr. Tousik Samui again, and he will talk today about interacting fields. And yeah, I have given you
No, not
co-host privileges. Now you can share.
Okay. Okay, let me start. Okay, for today's lecture, I have already sent the lecture notes to Rakim. Now upload it. And okay, so let me start that until now, let's say last 5 or 6 lectures, 4 by Ratul and 2 by me. So we were actually dealing with free field theory, where we don't have any interaction between the fields, only the kinetic terms and mass terms were present. Although that is very, very interesting to develop the formalism and all these things, but in a way, they are not very interesting for our physical processes or the interaction that we want to study. Okay, so for that we have to go little further, and we have to basically develop some more formalism to deal with these interactions and how we actually compute things that we see in an experiment or something like that. Okay, so that will be the key idea, and so we'll try to cover some of the calculations by tomorrow's lecture that will be helpful in like see that what happens with this QFT framework and what we can actually achieve and all these things. Okay, so let me start by in order to develop the formalism, let me start from two principles of quantum mechanics. That is like, so remember that this quantum field theory is formulated as a quantum theory. So it is based on the same principle. So if we write that star mark is that quantum field theory is based on the same principle of quantum mechanics. Okay, so that's the key idea, that even if it is a quantum field theory, of course, it is not twisted on all these things, but the basic principle that we do, like we use Hilbert space formalism to define physical states, and we compute expectations value of observables or of an operator which are Hermitian conjugates. So some important principle of quantum mechanics is physical states are actually represented by vectors in, of course, it's like usually it's called the rays because we can have some phase transformation, but I'm not going into those details now. So basically some vectors vector will be given for a physical state, and then we say that observables are represented by Hermitian operators. Okay, so these are the two key principles, and then actual observable, which we can see is given by the expectation value of that, let's say observable is O. It is basically the state psi and then the observable, and then psi. So this is not exactly the observable expectation value, but the square of it is actually the expectation value. But okay, so we will define this thing to be like quote unquote the expectation value, so that because the rest of the discussion is independent of the mod square. Okay, so this is the thing. Basically, what we can observe is this squared thing. Okay, so this is actually measured or observed, right? So this is the thing about the quantum mechanics. This there is a unique way to do all these calculations. There are like different pictures to or example in the we already know there are at least two different ways, let's say pictures to describe, and they are basically equivalent picture, the same system. So for example, in the Schrodinger picture, where we say that the state evolves over time, but operators don't. Okay, so this is the Schrodinger picture. In equation, we write that I del t psi, and since this is a Schrodinger picture, we will represent it. Let's say so time as h and psi of t is, so where h is the Hamiltonian of the system. Okay, and what happens, the operator, okay, so let us represent that by s, it does not evolve. Okay, so let's say OS. Let's say at a given time t0, it does not evolve, stays the same. The other picture or namely Heisenberg picture, so this is our picture, okay, where we say that psi t stays the same, okay? So it does not evolve. But the operators actually evolve. Okay, so let's say OH T would be e to the power I H T minus T naught, and then OH at T0. So let's say operator is given at T0. So these are the two ways, two different pictures, but both are equivalent in describing the same system. Only there is a like different viewpoint. That okay. So now, so by saying that it is describing the same system, meaning that in the Schrodinger and Heisenberg picture, our expectation value should remain the same, right? It should be the same. Okay, so in other words, if we calculate it in, let's say, Schrodinger picture, this will be t is OS and psi of TS, right? And then psi TS and T0 to be, so we are using, okay, so this, if we evolve, then psi T actually becomes, in this picture, e to the minus IH T minus T naught, and then psi of T naught, right? So we are using that relation here. This will be IH T minus T naught, and then OS to the minus IH T minus T naught, T naught, right? Now, if we identify, let's say, identify uh, or in other words, let's say the two pictures actually coincide, meaning that the states of Heisenberg picture and states uh, of the Schrodinger picture coincides at time t0, then we have this relation between the Schrodinger picture and the Heisenberg picture, and the relation is basically psi h okay, is equals psi t0. Yes. So because Heisenberg picture and Schrodinger picture coincides at t equals t0, then it will become I H t minus t naught and psi of t. Yes. Okay. So this is the relation between the Heisenberg picture and the Schrodinger picture in terms of the state, and the second relation between the operators are OH t would be to the IH t minus t naught OS to the power minus IH. So these are the two important relation between these two pictures. Okay, but we will do we will neither work on the Schrodinger picture nor work on the Heisenberg picture, but we will work on a hybrid picture. Hybrid picture called so how do we define this picture? So we have subscript capital I for this, and we will define this picture as similar to, let's say, the states are similar. So okay, so before that we have to define some more things. Okay, so in the quantum field theory, we already have seen that we have worked on the free field. So there are some good intuitions that we have for the free field, and we know how to create particles, how to annihilate and do certain computations of propagators and Hamiltonian and number operators, all these things. And so what we will do is basically, our approach would be basically to do the calculation as the interaction term as a perturbation to the free field theory. Okay. So our approach is to work in a setup where the interaction is a perturbation to the free. Okay. So now, for example, let us remember that one of the interaction that we introduced was L in the QED Lagrangian is essentially 1/4 if mu nu, if mu nu. So this is free field, free gauge field, and then psi bar phi del slash minus m. This is again free field, okay, free fermion field, but and this is, let's say, vector fields, okay. But then we have this interaction term L Q a mu psi bar comma mu psi, right? So, for example, this is our interaction term. Although this is in the Lagrangian, but we know how to come from the Lagrangian to the Hamiltonian density. So this, for example, is an interaction term. Okay. So this is one of the examples. So our formalism would be to approach this as the free field. So we will quantize the theory in a free field manner, and then use this interaction term as a perturbation to the free field. Okay. So in other words, if we go to the Hamiltonian approach, then our Hamiltonian density H should be written as H naught plus H interaction, where H naught is basically free Hamiltonian. Okay, so of course, anybody can split in any arbitrary manner, but since we have already developed the free Hamiltonian and free Hamiltonian formalism and free Lagrangian free field formalism, and we already know that how to create and annihilate particles and how to do the propagator, everything. So the best way would be splitting this H into free Hamiltonian plus the interaction term. Okay, so we will go in this form. Okay, and then our state, as I was mentioning in the interaction picture, will define it as e to the power I H naught t minus t naught and psi of t s. So it looks like somewhat like Heisenberg picture, but no, this is not exactly the total. Not the total Hamiltonian. Okay. So that's why this is a hybrid approach because we are not taking the full Hamiltonian here to get this thing, get the interaction states. Okay, and so once we do that, then we can immediately see that this is again at t equals t naught. Okay, these two states actually coincide. Okay, so that's another thing, that at t equal to t naught, as we said, that the Heisenberg states and the Schrodinger states coincide. Here also at t equal to t naught, they all actually coincide. Okay, so once we do this, do this, okay, define this, then we need to see that how the operators evolve or how operators are redefined in this manner. So now again, we'll go to that expectation value formalism. So expectation value at t should be seen as this. Let's say now the same operator is represented by the interaction OI in the interaction picture by OI. Okay, so then this should be, and using this relation, but we can see that this is this is Schrodinger, right? So now this should be OS, since this should give us the same result as the Schrodinger picture, and by equating these two, we can see that OI can be written in terms of OS as follows. So just quickly note this, that operators with the Schrodinger pictures are related by this, and the states are related by this. Okay, so these are the two things to remember. This looks like exactly the the Heisenberg picture-like picture, but just remember that here instead of full Hamiltonian, we are using only the free Hamiltonian here, H naught. Okay, so that's the difference. And now, if we try to see that how the state actually evolves given the state at T0 in the interaction picture, so then we can again go back to the equation, this one. Okay, so this equation, it's basically EI H naught minus T naught, and what was that? It's psi t, right? Now we know psi t is nothing but minus here it is the full Hamiltonian t minus t naught and psi t0 s, and now we know that at t equals t0, this s and I, the states are essentially the same, so it's this. Okay, so now we define this to be u t comma t0. So this is function of t and t0. So given h and h naught, okay, so this operator is defined as ut t0. Okay, so by which it evolves. Okay, so now our aim would be to find this operator. Okay, given h and h naught. Once we split the thing, then our aim would be to find this operator, and let us see how to find this operator. Okay, so another aside here is that how does this state evolve? So what will be the Schrodinger-like equation for this? Okay. So this state then will be like psi t I should be. So now if we differentiate in here, then we'll get I h naught t minus t naught, and here we'll get 1 minus h naught, because I squared gives me 1 minus sign, and with respect to t, it's like h naught comes here. Okay, and then we'll have from the second term, okay, from the second term, we'll have plus h, and it will be I minus I. Do I miss a minus sign? No, this I think is fine. Okay, so this is nothing but, if you remember, it's the interaction term, right? And if we kind of rewrite this as e to the I h naught t minus t naught h interaction to the minus I h naught t naught plus I h naught t minus t naught. Basically, this is identity, right? So because minus and plus in the exponent, and then the rest is e to the minus minus I h t minus t naught and then psi t naught I. Right? So now the last three term. Okay, let me write this way. So the first three, if you see, it is nothing but int of the interaction. So meaning that any operator which evolves like this, so if you remember OI, the expression for OI is this, okay? So this is essentially the Hamiltonian, interaction Hamiltonian in the interaction picture, okay? And the rest is nothing but psi of t in the interaction picture. If you remember, the psi it is basically this. Okay. Okay. So this is like in the interaction picture, the Schrodinger like equation and the evolution of the state. Okay. And then what governs the t0, the operator that we defined. So let us see evolution of that operator, or whether we can have a differential equation for the evolution of that operator. In practice, it actually goes as ut naught as I del t. This is nothing but it's like previously. Okay. And similar that we did here, if we remember the same way we did here, basically we we take the derivative in the similar fashion, then it will be H interaction and in the interaction picture and T. Okay, so the evolution of the ut t naught is given by this, and in principle, given the value of t at t naught, we can actually calculate ut in principle by this equation. And at t equals t naught, this matrix is actually identity, because if you place t as t naught in this matrix, it becomes exponent becomes 0. So this is basically ut t naught is identity. Okay. So we don't need to give the exact value of this operator at 0 at t equal to t naught, because it is already identity. Okay, so that we can. So this is in principle the evolution equation for this ut t naught operator. Okay, but solving this is not a very easy task because all these each interaction has time dependence, and so solving this is not that easy that we can diagonalize it and then evolve it, because every different time it has it is a different operator, even this h int at the interaction point. So every time you have to like rotate this and diagonalize it, and then actually evolve it. But that is a slightly difficult task. But thankfully, there is a solution, at least at least a closed form looking solution that exists. So the claim is that ut t naught is actually given by time ordered exponent of minus I t naught t image interaction. Okay. Sometimes. So did I citizen user. So DT and here each interaction at DT. Okay. And now from now on, we'll shorten this notation because it's writing it's a bit absurd looking. So let us shorten this as HI itself. Okay, so HI is not exactly the total Hamiltonian in the interaction picture, but it is the interaction term in the interaction picture. Okay, so that's how we will shorten this notation. Now come to this particular thing. We already have seen this this particular operator. It's called the time ordering. Okay, so we have already seen it, but we never in our earlier lectures we never saw the so why this was coming so frequently, or why we needed this. Now this is the first time we see that it actually comes because of this interaction picture formalism. Okay, so this is called the time ordering, and as we already know, time ordering means this means that that operators evaluated at a later time are raised to the left. Meaning that inside time ordering, let's say I have two operators, one is T1 and another is T2, and I T2 greater than T1. There is a clever way of writing this using theta function, but let us not go into that. Okay, so now let us try to like quickly prove this claim that that this U this unitary operator ut t naught is actually given by this. Okay, so for that we note two things. Okay, so note one is that inside time ordering, the operators compute. Okay, meaning that T01, T1, T2 is equal to T02, T2, T1, T1. Because this does not matter because in the end we have to place it when we bring it out of the time ordering operator. We have to place it appropriately using the okay. So this is note one, and note two is that del t actually commutes with time ordering. Okay, so O1, let's say O2, and On, okay, is equal to T del T and O1, O2. Okay, so this is not very easy to see, but let me sketch this proof that del. So this one, let's say del T On. Okay, so let's say after time ordering, they become OI1, OI2, dot OIN, meaning that so let's say its argument is T1, this is T2. Explicitly rented. So meaning that once it comes out of the time ordering, okay, so it has already been arranged with these indices. Okay? So that meaning that Ti1 is greater than Ti2 is greater than. So the appropriate permutation has been taken to ensure the time ordering is maintained. Okay. Now, once you differentiate it, then it is I1, Ti1 is prime, and then the rest are the same, OIN plus. Using the chain rule, you have to differentiate the second one, so OI1, and then O prime I2 at T I2, and so on and so forth. And then it will be like in OI1, OI2, and then O of IN prime at T. Okay, so this is the this will be the expression on the left hand side, and on the right hand side, if you do, so this is LHS. On the right hand side, if you do, you can convince yourself that since after the differentiation you keep this time same, you have to order exactly equivalently, and hence the LHS and RHS should be same. So if you take this, let's say O1, O2, ON, then you take O1, O1 prime, O2 plus O1, O2 prime, ON. And now once you take the time ordering for this, time ordering for this, time ordering for this would be the same, because I1 prime, I2 ON, so and so on and so forth. Okay, so this says that okay, this del T and T actually is equal to del T and the operators. Okay, so these are the two nodes. With this, we can actually show that this U T0 is the time ordered of exponential minus 5 T naught to T. Now we are writing it as HI, okay, of T prime. And now, so this, what is this exponent? Exponent is basically identity, this usual like okay, the same problem. So everything vanishes. Anyway, let me finish this, then we can take a break. And okay, so with those two notes, which has already vanished from my iPad. Okay, so let me write what I was writing. Is, let's say, time ordering of exponent of minus 5 T. dt prime is nothing but time ordering of identity and minus I integration t naught t h I dt prime t prime minus I square. So this will be plus then, and then t naught t dt prime t naught t double prime. Sorry. This d double prime, and then h t prime, and so on and so forth. Okay. So now if we take the derivative of this, let's say we define it to be O, then I del O del, sorry, this is U. This is U, then del U del T is I del D of time ordering of the whole thing. And now since I can put it inside, it will be time ordering of I del T. The first term will give me 0, 0. Second term will precisely give me identity. And the second term, so there are actually two HIs, okay? So only one of the HI come out. Let's say third term will be what? Minus I over 2. And since there are two things after chain rule, we will have a two factor, and one of them will basically come out, and this will be T, the other will be just like T and T prime. And now here again, we are doing everything inside the time ordering, okay? Inside the time ordering. So it does not matter where this operator was, because in the end, if even if it were like on the right side, so basically what happens that if we define do the derivative with this, then it comes in front. But if we derivative on the t double prime, it goes back. But within time ordering, the order does not matter that we actually claimed earlier. So this stays the same. I'm sorry, this will not be identity. This will be HIT, right, after the differentiation. And then if we do a small calculation, then it will be HIT. Now, since T is the latest time available in the whole series, so we can take HIT out of the time ordering to the left and out of the time ordering, and then it will remain the exponential of minus I integration T naught to T HI time. Okay, so this is the proof that this again is ut t naught. So this is the proof that if we define ut t naught as this way, let's say time order of exponential e to the power minus I t t naught to t hit dt, then it actually follows the evolution equation that we derived. Okay, so this essentially tells us that we have kind of found a solution to ut, which is explicitly time ordering of exponential of minus I integration t naught to t dt prime h. Okay. So let me stop here for question and answer, and then I'll continue. Okay. Hello. Let me see if
Yeah, if anyone has any questions, you can raise your hand as well.
there was a minus sign confusion. I don't know which slide of which part. Okay. Hare Krishna, you have been allowed to speak.
Sir, on the O interaction term, there is, I think there is a minus sign.
Which terms, right?
I mean, scroll the page upside.
Mm-hmm.
Yeah, there's a
Here?
Yeah,
It's
the minus sign.
so here, right?
Yeah.
Right.
Okay, thanks.
Okay, so can you please explain the second line in the present slide? Okay, so at that point, the present slide was this, but which one is the second line? Okay, so our claim was that, let me explain it again. Our claim was that the expression for U operator is given by the time ordering. Okay, this is ordering, and then exponential minus it not to t dt. Okay? This was our claim. In order to prove that, what we did is like we take the derivative on this. Okay, so take the derivative on this. Put in a different color. Okay, so take the derivative on this and try to show that it gives the evolution equation of ut t naught. Okay, so that was unfortunately this equation that we wrote has been erased because of the glitch that I have in this in my iPad. But this was the evolution equation, if you remember, for u t. And from our claim, we did take the derivative and arrive at the equation of motion or equation of evolution. Okay, if there is no more, what's the time now? Okay, so as usual, I will start at maybe 8 o'clock. We can have like 5-6 minutes, right?
Okay, I'll pause the recording then.
So, okay, so let us see that so far what we did is like find out this evolution operator, which actually gives rise to the evolution of our field, of our state in the interaction picture. Okay, so far what we have kind of derived is sign of t in the interaction picture is given by ut t naught and of sign. In the interaction picture, we u naught as is given by time ordering of exponential of t minus I and then I. So, since we now identify it as HI prime, so now let us see some utility and for which we need some interacting Hamiltonian, or let's say Hamiltonian that we can actually calculate from Lagrangian also. So let us take a very simple and toy theory to see some of the examples. So let us take example theory, which is scalar Yukawa theory. And the Lagrangian for this theory, let me write it down as, okay, so now we want to see the utility of this formalism that we develop. So we're not caring about the actual theory, but we are trying to show some use cases with some example easy through. Okay, so where so this is the Lagrangian, and then with a half factor here. Minus m squared squared. So all these are free, and then the interaction term, let me write it in a different color, is actually so this is the Lagrangian density. So where say that psi star basically are complex, and phi is a complex scalar field. This is of course a toy theory, but we want to see the utility of the formalism. That's why we are using the toy theory. Okay, and so usual mode expansion that we had is psi of x. Okay, is given by let me write it carefully. E to the power x. Let me write it precisely. Let's say this state, since we want to start from t0, let's say this state is given at t0. Okay, and then psi dagger, of course, is minus I. And phi of x. So, okay, so for okay, for the function factor, it's actually this. Since this is a scalar field, the same creation. Okay. So this is this thing, and then of course the if we calculate the density, Hamiltonian density is and the interaction term only, then it will be effectively because we don't have any kinetic term in the interaction Lagrangian. So the interaction term at least will be minus Li, which is nothing but G psi star psi. And all of them are actually at the same space-time point. So this is x, x, x. So that's, and now let us try to calculate with this. Let us try to calculate psi I. So this is in the starting picture that we define all this, these three. Then we have to appropriately like define the interaction picture state, right? So psi I T naught x will be, if you remember, for the operator. So since these are the operators, psi, all the signs are the operators, so it will follow this equation. Okay, so the operator equation is here. Okay. This one. So we have to kind of use it here. So it will be, so remember psi is here. So now the interaction picture, it will be e to the I H naught E minus T naught, and then psi E naught x and H minus T naught. Okay. So now let us take the, so it has the integrations and all these things. The essential part, let us do the essential part where we have the operators and then plug that in into the actual. So this is the non-trivial part because of their because they are operators, and the commutation and anti-commutation, all these things has to be taken care of. So essential part from the first part, let's say from this will come out, right? Let us try to calculate this. For this, we already know that that H naught, and since this is annihilation operator, B is an annihilation operator, their commutation is essentially minus sorry, and which is defined as omega also. Okay. So this is the, and the other commutation relation. Let me write it. So now, if we know this, and then we have to invoke another identity called or formula called Baker-Campbell. It's not exactly the Baker-Campbell, but formula which says that if I have an operator which is like E minus A to the power B, where A, B, and A, B are the operators, then this is given by identity plus A plus 1 over and this way. Now, thankfully for our case, this B is nothing but IH naught B minus T naught, and A is B. So we know this has for our case it will be I minus I, which is a scalar number, T minus naught, and then we'll have BP back. Then again, when we do B comma A, we can recursively use the since B commutator A is proportional to BP, then we can recursively use it. Okay, and then this expression actually becomes identity minus I E minus naught and BP and I times factorial square. So whole thing that will come out is this, and then it will become minus I T. This is easy to show, and once we plug this back into the expression, I so from the first term, we'll see that it will become integration. Yes. Mm-hmm. And then we had BP already here. From this evolution, we'll have EP dot T minus T naught. And we already had plus I P dot X. So combining these two will become C part also. It will be I minus I. Right? So this is nothing but minus I. Now this is 4 vector, and then CP vector I is where it's not is essentially T minus T. So this will be the expression for psi T. Similarly, psi I dagger would be QP Q 1 over square root P, and will be CP given I minus IP dot X plus and phi in the introduction picture will become so this is E for psi, this is E for psi, but this is E for phi. These three E's are different. So, we can write it in the same way. It's not matter. So these three will be the fields in the interaction picture will become basically this. From the Schrodinger, we now have the fields in the interaction picture. So what we are interested in is basically we know how to let's say create particles in the sense that by the creation operator we can create the states. But then let's say it evolves via the evolution equation, basically through this operator u, and then we want to see that how it evolves, and then finally where it reaches to. In other ways, our aim basically is to compute the probability, let's say probability of evolving initial evolving an initial state, let's say I to a final state. For example, so if we ask this question that, okay, I have an initial state I, which I know how to get. So let's say I is given by, okay, so that let me come to that later. And then if I want to ask that, what is the probability that it will finally evolve to the state F? So that is we kind of are interested. Okay, so now let us do it more concretely. Let us say that, okay, I have a state which has two sides in it. Okay, so this is, let's say, initial state, and then let's say we want to see that this goes to itself but with a different momentum. So psi psi, and this is the final state. And what is the probability of this scattering? Let's say if this is a scattering, then we are interested in, let's say, two psi collide or comes together and gives rise to two different sides with different moment, the same side but with different momentum. So what is the probability of this scattering happening? Okay. So this is one of the things that we can be interested in, or to some other particles also, since in the quantum field theory setup, we know that the number is not conserved. Or maybe what we are interested in, let's say we have a phi particle, and let's say what is the probability that it actually decays to psi particles. So this is initial state, and this is final state. So for this problem, our initial state then will become nothing but with initial state will be two particles which are actually created from vacuum with the dagger, let's say P1 dagger, and the second particle has a momentum, let's say P2. Okay, and with appropriate, let's say, normalization that we saw that this is right. For this initial state is this, but for the final state, it can have different momentum than our final state. Is to be, let's say, P2 prime, since this is a different momentum now, and created out of that. So, for example, this one would be, let's say, for this, but let's say for this, then my initial state is slightly different. Okay. So this is my initial state, and this is my state for this problem. But for the other problem, let's say would be, let's say, my initial state is I, but now this is only one particle. This is created, the dagger, and my final state is the same as the final state that we had. This would be fine. Okay, so here actually we cannot have psi psi together. We will have psi and psi star. We have to have that, and that's why it will be like it will not be B, it will be C. So now these are the questions that we are kind of interested in. Okay. Anyway, so those are the questions that we are kind of interested in this set. Okay, so now of course we can create the initial state I, and then it will evolve into something ut let's say plus, and from t minus point, and it will evolve into certain thing. So this is like from t minus to t plus, where this is the initial time and this is the final time. Okay. Now, once we have this, then we will ask that, okay, so now what is the probability that it will give me a particular final state? In that case, it will be like if u t plus t minus I. Okay. So now what we will assume in this case, this is slightly sketchy, but we can have a like better formalism where it will come as a like a normalization factor, but where we assume that this t minus is basically minus infinity. That means when my theory was free, they were not interacting, and t plus is essentially a plus infinity. That is, it is again non-interacting theory, but in the middle they came together and has some interaction for a brief moment and gives rise to the final state. Okay, so that's the idea that it will be. Now, once this we want to calculate, and we already know what my initial state is, what my final state is. These let's say we have the idea, and once we do that, then and also we have the expression for ut plus and ut plus t minus, and then the calculation is straight. So once we try to do it, is basically f of t, and so then my t plus is nothing but time ordered and exponential of minus I t naught to t h interaction t prime. So we kind of have everything at our hand. We know how to formulate this I or initial state. We know how to formulate. We know how to formulate the final state if, and we also know that this Hamiltonian, since this Hamiltonian is basically function of the fields, the operator of the fields, and we know how to write those fields in the interaction picture. So we have everything. We have everything at our disposal but not. But the computation is a little bit challenging because let us try to see how this goes. So this will go as identity. Then the first term is t minus to t plus, and then e dt. So we have also here. And so on and so forth. But problem comes when we try to calculate this thing. Okay, so first part is not that interesting because this is the identity operator, and then we are kind of not interested of a particle evolving to itself. So that we are not interested. But let's say if we are interested in the second term, okay, so then it is time ordered of minus I t minus t plus hi dt. In principle, we can calculate it, but remember that this hi, at least in our example, has three different operators. Okay, so one is psi star operator, I, then we have psi operator, and then we have phi operator. Okay, so now taking the time ordering and doing all these possibilities, that's okay, where this time come from, and all these things is actually a slightly challenging task. And fortunately, we have a very good theorem which is goes by the name of Weeks. It's called Weeks theorem, by which we can make this calculation actually very simple. So now we will discuss some importance of the Weeks theorem. So before that, let me say that let us see that we have a, let's say, scalar theory. So we have phi, which has the phi x term and phi minus term, where phi x, phi plus is given by dq. But unfortunately, in this interaction picture, the plus comes as a minus in the exponent. So this plus and minus has be defined in the earlier lectures as a plus and minus here in the Schrodinger picture, but now in the interaction picture, they the opposite. Okay. Remember. Okay, so this plus represents creation, so minus represents creation part. This represents direction. Okay. And then let us see one example before stating the Weeks theorem. This is the connection between the time ordering and the normal ordering that we define. Let me first define the normal ordering. Okay. So time ordering, we have already defined that the later time comes to the left. Okay, so normal ordering is of operators is in, let's say, O1, O2. Okay, just write it down and then explain. Normal ordering, meaning that creation operators so now there is a connection between the time ordering and the normal ordering. Okay, so this meaning that normal ordering, let's say, of many operator AP, BP, dagger, CP, CP, dagger. This means that all the creation operator will come to the left, and all the annihilation operators will go to the right. Okay, so this is one example when what normal ordering does. Okay, so it's basically brings all the creation operators to the left and all the annihilation operators to the right. In other words, if we write in terms of this 5 plus and 5 minus, so all the 5 minuses to the left and all 5 pluses to the right. Okay, so let us see one example with time ordering and connection between so tx plus y. Let's say if we do it, minus 1. 5 plus y plus 5 minus y. Remember that we have broken it down into pluses and minuses, because pluses contains the annihilation operator, minus contains a creation operator. Okay. So now if, let's say, x naught is greater than y naught, then what happens? The time ordering means that this will come first and this will come second. So that is because the x naught, the time component of x is at a later time. Okay. So in that scenario, it will become 5 plus x plus 5 minus x and times 5 plus y plus 5 minus y, right? And then if we do it this way, 5 plus y, the simple multiplication times 5 minus 1 plus 5 minus x 5 plus 1 and then 5 minus x 5 minus 5. And if we look at carefully, this all has annihilation, right? Okay, this all has creation operators. So these already are time order. 5 minus has creation and 5 plus has annihilation operator. Okay. So these two are already normal order, and then 5 minus and 5 plus, this is also normal order because the creation is on the left, and so only thing that does not have the annihilation operator to the right is this operator. So what we can do is do a trick like, okay, so we will write this as 5 minus y 5 plus x plus commutator of 5 plus x 5 minus y. So this is the trick that we can do. Now we can see that that Okay, let me write it explicitly. Six plus 5 minus 6 5 minus 6 5. Okay, so this whole thing is normal order of actually 5 x 5. So if you calculate the normal order of this thing and expand it accordingly, then you'll see that this will get this 4 term. In addition to that, we are getting an extra term, which is 5 minus 1. Okay, so this is for x greater than x not greater than y naught. Okay, so now if we actually look this thing, 5 plus x and 5 minus y. Okay. So that if we want to calculate, it's if you remember the definition, it is nothing but d cube p over cube and 1 over square root p cube prime 1 over square root prime and then exponentials I dot x dot y, and then we have the commutator between a and B. So because this contains the annihilation operator and this contains the creation operator. So this is the expression. The rest are like the integration variables and all this. And the measurements. Okay, so now we know that this number, this quantity is nothing but 2 pi q. If you remember our commutation relations, then this is nothing but this is nothing. And if you use that expression and integrate over, let's say p prime, then all the p prime will be replaced by p, and this let's say 2 pi and we will have dqp over 2 pi q goes away with p will be 10. Then we'll have e to the power 5 p dot x minus 1 and nothing else. Okay, so now if you remember, it does not have any operator. It is a C number. Okay, so that's the beauty of this ordering, that okay, so if x naught greater than y naught, then phi of x, phi of y, or at least for the real scalar field, it's nothing but the normal ordering of phi x, phi y plus this commutator, which is a C number, and if we remember it, it's nothing but the propagator if x naught is greater than. Okay, so on the other hand, if it were the other way around, that is y naught greater than x naught, then it is nothing but it's the same normal ordering. Okay, here we don't have any change, but only thing that we had to have was like instead of this term, instead of this term, instead of the stop responding. Sorry about that. Okay, so what I was saying, if it were like y naught greater than other way around, y naught greater than x naught instead of the term here,
In your reporting procedure, employer what 2 years certificate for foreign officer training assistant. Constantly public of travel institution with the government of the university.
again, yeah. So instead of this term, the commutation has had to be taken second term, and then it would have been like d of y minus x. Okay, so now if we again remember that the combination combining this dx minus y and y minus x gives us the Feynman propagator. So eventually we would be like getting p phi x time order of two operators is nothing but normal order of phi 1. Then it will be Feynman propagator x minus y. Okay. So that's with one example we showed the Wick's theorem. But now let me now now state the Wick's theorem formally. Okay, so says that time ordered product of many operators, let's say, I'm not going to prove this, it's slightly I mean time consuming task to prove this, but let me state it anyway, is equal to normal order product of those in operators and normal ordering of all possible ways of contraction. Okay, so now let me define the word contraction. Where contraction of a pair of field is essentially replacing them by Feynman propagator and leaving other fields untouched. Okay. So basically contraction means that so what we did here, that we remove the two fields, the contraction between two fields is like remove those fields and replace it by the Feynman propagator. Let me give some examples. Is like let's say we have four field phi 2, phi 3, and phi 4. Okay, and this means that if we write it, it will be normal order of phi 1, phi 2, phi 3, phi 4 is here, this one, and then normal ordering of all ways of contract. So how can you contract these four fields? So one would be like keep phi 1, phi 2 as it is, and phi3, phi4 contract. So this is one possibility. And now since we have four fields, two fields contraction there will be six pairs to do. So let me write them explicitly. Let's say phi3, and then it will be phi4, phi2, and phi4. So remember that I can easily move it out because this is a C number. This is after the contraction. It is basically the Feynman propagator. So it's not an operator anymore. So I can move it around anywhere I want. Then it will be yeah, I think I have to stop now because this is not working. Anyways, going to stop. After this, maybe I can start from here tomorrow. Okay, let me see. Oh, it's a- that's normal ordering of 1, 2, 3, 1, 2, 3, 4, 5, and then oh, which will be 5, 3, 5, 4. And then again, I can contract two pairs. So this first set of six operators, like one pair was contracted and others are like it's still in the normal ordering. But now what we can do is try to contract two pairs. So that will be phi1, phi2, and phi3, phi4 contraction. Then phi1, phi3 contraction, phi2, phi4 contraction, and phi1, phi4, all possibilities. Okay. So okay, so this is the thing. So this is basically Week's theorem, and now we already know this contraction means it is equal to the Feynman propagator of let's say for any ij is ij is basically IMC. So if I propagator of xi minus xj, and this Feynman propagator is given by for the scalar field. Let's see the expression. Okay, so this is this thing. So now, as I was mentioning, that our aim was to calculate something like this, and from this we were getting some time ordering of phi 1, phi 2, etc., etc. And now we know that this can be written in terms of the normal ordering plus normal ordering and contraction. And what happens that since this is normal ordering, once the normal ordering is defined, it has the special property that the annihilation will go to the right and accretion will go to the left. And hence the dealing with this particular quantity will be easier, and then we'll have bunch of Feynman propagators, C numbers, and dealing those will be easier. Okay, so maybe I will stop now because of it's already late, and so tomorrow we will like discuss some of the one or two examples from this theory or from QED, and try to see how this computation works. Okay, so I'll stop here and I'll wait for questions.
Okay, thank you. I'll stop the recording.